We learned in chemistry that energy is always conserved. This is the first law of thermodynamics, where energy cannot be created or destroyed, it only changes forms. So in this class, majority of your energies are going to be kinetic, potential, due to gravitational, potential energy, and spring energy. The main forms of energy we discussed was kinetic energy, abbreviated K or KE. Kinetic energy is any energy in motion. The general formula for kinetic energy is 1/2 mass times velocity squared. So KE equals 1/2 mv squared. The units for mass is kilogram. The units for velocity is meters per second. And you need to square it. So if I simplify that, that becomes kilogram meter squared over a second squared, which is also a joule. Since we know that energy is conserved, we could do work and make things move. This is called the work-energy theorem, in which work is equal to the changing kinetic energy. Remember, delta, the change in, means final minus initial. So when I have a change in kinetic energy, I could expand that out as kinetic energy final minus kinetic energy initial. Work is also force times distance. So if I plug in for kinetic energy, that is 1/2 m vf squared minus 1/2 m v naught squared. I could simplify this even further if I wanted to. Take out the 1/2 because that is the same in both of my quantities. I could also take out the mass. So if I simplify that, that will become 1/2 m parentheses vf squared minus v naught squared. This is equal to work, and work is force times distance. And remember, this must be parallel. The first problem we're going to do is the following. A 50-kilogram bicyclist on a 10-kilogram bike speeds up from 5 meters per second to 10 meters per second. What is the work done to increase the speed? The first thing you should do is identify the variables. So we have a mass of the bike as 10 kilograms. We have the mass of the bicyclist as 50 kilograms. We know the speed goes from 50 to 10. Remember, in class we said from is usually the initial. So V initial is 5.0 meters per second. 2, which is our final, which is 10 meters per second. What is the work done? So we're looking for work. So the only formula that we know that has work and velocity and mass is the work-energy theorem. So work is equal to change in kinetic energy, and we know kinetic energy is KE final minus KE initial. So work is going to equal to 1/2 mass velocity final squared minus 1/2 mass velocity initial square. So you could either plug in the numbers here, or you can simplify it a little bit further. 1/2 mass velocity final squared minus velocity initial squared. Now I'm going to plug in. So this is 1/2, but the mass is the total mass because the bicyclist has mass and the bike, and both of them are increasing in speed together. So I have to do 10 kilograms plus 50 kilograms. My V final is 10 meters per second. I need to square that, minus my initial, which is 5 meters per second squared. And I need to put brackets around this because this is parentheses. I took out the mass and the half. Now I'm going to simplify. So this is 1/2. 10 plus 50 is 60 kilograms. Now I need to do my parentheses work here. 10 is squared, so that's 100. Minus 5 is squared. You must square first before you subtract. So 100 minus 25 is 75. So this equation becomes 1/2 times 60 times 75, which is 2,250 joules. So identify your variables and then an equation will come out. The mass is equal to 0.075 kilogram. A force is applied, but we don't know what that force is. We're going to look for that force. A distance is given as 0.90 meter. It states that the bowl leaves at 40 meters per second, but we want the force that is applied to cause this bowl to leave at 40 meters per second. So that means the initial velocity has to be 0 and the final velocity has to be 40 meters per second. So the only formula with these variables is the work energy theorem. So I could expand kinetic energy final minus kinetic energy initial. I could already cancel out initial. Why? My initial velocity is 0. I need to expand force times distance for work because they're not looking for work, they are looking for force. Kinetic energy final is just 1/2 mass times velocity final square. I need to solve for F. Since F and D are multiplied, I'm going to divide onto both sides. So F is equal to mv final squared over, I'm going to bring this 2 down, so it's 2d. So if I plug this in, this is 0.075 kilograms times 40 meters per second squared divided by 2 times the distance, which is 0.90 meters. Simplifying this becomes 66.67 newtons. Units of force is in newtons. Pause the video, draw the picture, identify your variables, and figure out an equation to use, and solve it. Then check your answers. 1,500 is the mass of the car. It is driven off a 50-meter cliff, so that is your distance. It was going 20 meters per second when it jumped off the cliff, so that is your V initial. So we are looking for our V final. So if I draw my picture, this is what my picture looks like. My height or my distance is 50 meters. The car goes horizontally at 20 meters per second. And I am finding its final velocity at the bottom. There are 2 ways you could solve this problem and get it correct. I'm going to do it both ways. The first way I'm going to do this is the work kinetic energy theorem, which is work is equal to change in kinetic energy. This is equal to KE final minus KE initial. Work is also equal to force times distance. Since this car is falling and there's no air resistance, it is under the influence of gravity. So the force here is the weight. So the weight is mass times gravity times the height d. This is equal to kinetic energy final, which is 1/2 mv final squared minus 1/2 my initial v naught squared. I'm going to simplify this because if you notice, all the masses cancel out. Why? There's a mass here, there's a mass here, and there's a mass in the last quantity. So my equation becomes GD equals to 1/2 V final squared minus 1/2 V initial square. I could take out a half, factor out a half, or I can multiply everything by 2. So if I multiply this part by 2, because opposite of division is multiplication, I need to multiply this side by 2, the left side. The halves cancel out here, and so it becomes 2GD equals to V final square minus V initial squared. And since I'm looking for V final square, I need to move the V initial to the opposite side. Since it's subtracted, I need to add a V naught squared to both sides. So when I do that, V final square becomes V naught squared plus 2GD, and then I have to take the square root. So V final is equal to, now I'm going to plug in 20 meters per second squared plus 2, gravity is 9.8 meters per second squared, times the height, which is the distance, 50 meters, and I take the square root of this, which equals 37.15 meters per second. The second method I'm going to use is also conservation of energy, but I'm going to start this off with mechanical energy initial is equal to mechanical energy final. We know since we have height and we have velocity, the two possible energies are kinetic energy initial, potential energy initial, kinetic energy final, plus potential energy final. Initially, I have kinetic energy, y, it's leaving at 20 meters per second. I also have height. At the end, I have V final because I am looking for V final, but I have no more potential energy because it already fell to 50 meters. So now my equation is 1/2 mass velocity squared plus mgh initial equals to 1/2 mass velocity final square. All the masses cancel out, and I'm looking for V final, so I'm going to multiply everything by 2 because I need to isolate V final. So if I do that, the 2 cancels out here with the half. This becomes also, the 2 cancels out with the half. And so this becomes V naught squared plus 2GH naught equals to V final squared. And then I have to take the square root. The square root, if you notice, this is the same equation as the previous one. And this makes sense. Remember, when we did work, we said work was force times distance. Since the car was in free fall, the force becomes its weight. And if I plug in for mg and d, this is the same thing as mgh. So this is potential energy. And that is what we began with. In general, if you have a height difference, it is easier. Mechanical energy initial equals mechanical energy final. If you notice, we didn't care what direction it went. If the velocity initial went to the right, but it dropped vertically, it is because energy is scalar. We don't want to account for direction. There is no x and y. Conservation of energy states the total energy is constant. That means the E initial must equal to E final, or the mechanical energy initial must equal to the mechanical energy final. So the three possible energies that you could start and end with is kinetic energy, potential energy, and spring energy. You only include spring energy if a spring is present. If not, then it's just Ke plus Pe equals Ke plus Pe. So in this example, a car went up the hill until it stopped. So it started with 100 meters per second, and we're finding the maximum height. So we know that energy is conserved. So we're going to start with E initial equals E final. The two possible energies that we can have is kinetic energy, because there is speed or motion, and potential energy because there is height. There is no spring, so we do not include it. So we could also have kinetic energy at the end and potential energy at the end. So if I look here, my initial velocity is 100. So I know I have kinetic energy, but I have no height. So that's going to cancel out. At the end, the car comes to a stop. So there's no kinetic energy. So all I have at the end is potential energy. Now I substitute in for kinetic energy, which is 1/2 mv naught squared equals to mgh. The masses cancel out. So h, I need to isolate it, divide by g on both sides. When I do that, the g's cancel out here. This becomes v naught squared. I'm going to bring the 2 down because the half is in the denominator. So that becomes 2g. This is equal to h. So this is going to be 100 meters per second squared divided by 2 times gravity. This is approximately 510 meters. So quick summary. When we use work, the formula work is equal to F times D. Force and displacement must be parallel to each other. If they are not parallel, use cosine or sine to make it parallel. When we have conservation of energy, the only types of energy that we will have is kinetic, potential, and spring. If something is moving, it's going to have kinetic energy. If something has height, it's going to have potential energy. If there is a spring, you're going to have spring energy. And the last thing, we don't account for direction. Direction is only if it's a vector. Energy is a scalar. The only time we do x and y, remember, is for force, because force is a vector.